we're going to start off our tour of objects in the universe by talking about very small objects. Now, I even put them in the same category as stars, but they're not actually going to ignite. So they're not going to turn into a star, and that's the reason why I put that thing in quotation marks there. So these are very small objects. So how small are they? So that they're going to be less than 8% the mass of our sun. Anything less than this number is going to turn into this kind of an object. All right, so the first statement says that the mass of this object is going to be insufficient to generate the pressure necessary to generate the 10 million Kelvin in the core, and so this object will never have thermonuclear explosions. So let's review here that mass causes gravity. So we've got the force of gravity. The larger the mass of a star, the greater its gravity is going to be. Okay, then we have that the force of gravity is going to cause pressure. Okay, because pressure is equal to force divided by area. So the greater the force, the greater the pressure is on it. Okay, then we can go down a little bit further and we can say that the greater the pressure on a star, the greater its temperature is going to be, because we're going to use the ideal gas law. Pressure times volume is equal to the number of gas molecules and then a constant and then T. But the main thing you should see is if the pressure goes up, the temperature goes up. Okay, and then the higher the temperature gets, eventually, if we can get to this magic number of 10 million Kelvin, then the elements of hydrogen inside of this star will smash into each other. You'll have nuclear fusion, and it will start to turn into helium. Okay, so think that mass is ultimately what's going to be causing the nuclear explosions. But this object is not going to have enough mass to generate enough gravity, to generate enough pressure, to generate the 10 million Kelvin needed for ignition. So this object is going to be called a brown dwarf. It's going to have a diameter of anywhere between 1 times the diameter or radius of Jupiter up to 4 times the radius of Jupiter. So Jupiter we can consider to be an example of a brown dwarf. Now there's some astronomers that say no, that's not true, because Jupiter is in orbit around the sun and is a planet, whereas these brown dwarfs are things that need to form at the same time as the sun does. Well, it's a matter of what you want to call it. So I'm going to say that Jupiter is a failed star, that if Jupiter had had more mass, Jupiter would have ignited and turned into a small star. It would have been visible during the daytime, but it's not like it would have given off too much heat onto the Earth. The density is going to be of these brown dwarf things is going to be the same as the density of Jupiter, and the gravity of this object is going to be countered by thermal gas pressure. Okay, so now we need to talk about what do we mean by thermal gas pressure. Okay, so let's go into our notes to another thing here. This one here. So reasons why stars do not collapse. Anything that has mass is going to have gravity. Gravity always wants to crush the object and turn it into a black hole. So let's say that we're talking about a hot air balloon. So if you have a hot air balloon, why doesn't that hot air balloon just collapse and turn into nothing? Okay, it's because the air molecules inside the hot air balloon are moving at different speeds and in different directions. So I'm indicating that with arrows. So a big arrow means it's moving really fast. A little arrow means it's not moving so fast. So all of these air molecules are moving in different directions. And when they hit the sides of the balloon, they're exerting a force on the balloon. And they're exerting a pressure on the balloon. So we're going to call this thermal gas pressure. It depends on the temperature. So if you raise the temperature of the air molecules that are in here, they start moving faster. And the faster they move, the harder they hit the edges of the balloon, and they exert more pressure. So it's a temperature thing. So that thermal gas pressure depends on the temperature of the object. Okay, so let's go back to what we were talking about here. Okay, and so eventually though, the temperature is going to go to absolute zero. So think about what's going on inside of Jupiter right now. In the core of Jupiter, the temperature is approximately 20,000 Kelvin. Now, is that enough for ignition? Oh no, no. No, the temperature in the core of Jupiter would have to get to 10 million Kelvin before it would ignite. But Jupiter only has a temperature of about 20,000 Kelvin, and so it's pretty hot in the center of Jupiter, but not nearly hot enough for thermonuclear explosions. So Jupiter is cooling off. Jupiter is giving off its heat into outer space. And as it does so, Jupiter is shrinking. It shrinks at a rate of about 1 centimeter per year. So the radius of Jupiter is getting smaller, just like if you were to take a hot air balloon, and as it starts to get colder, it's going to start to shrink. You can try this in your refrigerator. So if you were to blow up a balloon, look at the diameter of that balloon, then stick it in the freezer compartment, and then look at it 24 hours later, you would find that that balloon has shrunk. So similarly, Jupiter is going to shrink. Now this is going to take trillions of years for this to happen. So trillions of years into the future, and remember, the age of the universe is only about 12 to 14 billion years old. So in trillions of years, Jupiter is going to shrink down to a very, very compact object. We're going to call this thing a black dwarf. So a brown dwarf turns into a black dwarf eventually when it reaches absolute zero. The diameter of this object is going to be about the radius of the Earth. The density of this object is going to be equivalent to taking 10 elephants, putting them in a blender, and then squishing them into a glass. So that was going to be the density of this black dwarf material. And gravity is going to be countered by electron degeneracy pressure. Notice it is not countered by thermal gas pressure because the temperature has gone to zero. So that means that these molecules in here, they can't move anymore. They're not moving because they don't have any kinetic energy, because that depends on temperature. So now we need some other kind of force that's going to keep this object from collapsing and turning into a black hole. And that's going to be electron degeneracy pressure. So let's take a look at what do I mean by that. Okay, so now we're talking about the electron degeneracy pressure, which is going to keep white dwarfs and black dwarfs from collapsing. And this gets back to the idea of the atomic hotel. When we talked about atoms, we said that an atom has different energy levels to it, different floors where the electrons live. So let's imagine that you've got one of these hotels and another hotel over here, and they're getting closer and closer and closer together. So as this object here is collapsing, the atoms are getting closer together. And as they get closer together, let's say that the electrons on one of these things over here, which is at a high energy level, says, I think I'm going to jump over onto this one and live on a lower energy level. Okay, but this atom over here is going to say, oh no, you don't, because according to the rules of quantum mechanics, only a certain number of electrons can live on the floors, and you're not allowed to. So we're full up. We won't allow any more electrons to live with us. So that's going to keep these atoms a certain distance away from each other, because if they get any closer, then electrons would be trying to live in places where they're not allowed to live. Okay, so this is going to be called electron degeneracy pressure, because it's the electrons that are determining it. Okay, now one other thing I did want to show you here about this was, you can see there's the picture of Jupiter, and then underneath it is this hypothetical picture of what a black dwarf would look like. And it's going to be about 1/10 the size of Jupiter. Now, I really did not have a good picture of what a black dwarf would look like. So if I expand this thing here, you can see there's the original picture that I got from the internet. Well, we don't have any pictures of these black dwarf things because there's not one of them in the universe. There are no black dwarfs in the universe currently, because it's going to take trillions of years before one of these things forms. So we didn't have a picture of one, but that didn't stop me. So I went to the internet and I looked up the movie The Fifth Element, okay, the one with Bruce Willis. And so do you remember that there was this creature that was trying to destroy the universe? It was ultimate evil, and it looked kind of like a planet. That's it there. I thought it looked pretty cool, and so if there was a black dwarf, then that's what it would look like. All right, so let's take a break, and when we come back, this time we're going to discuss what's going to happen to small stars. See you in just a moment.